Hello and welcome back to Data Analysis and Visualization. I'm Javita Christie, and in this video, I'm going to explain to you decision trees and random forest algorithm. So let's begin. First of all, what are decision trees? So let's take a look at this data on the top. It's a simple scatter plot and it does not contain a lot of data points, as you can see. So there are some data points which are blue and there are some data points which are yellow squares. So to separate the classes, we don't necessarily need a fancy hyperplane. So this is something that is done in a support vector machine algorithm, which I haven't explained in any of the videos, but maybe in one of the future videos we could discuss that. So you don't need to create a line or anything to separate this data, a hyperplane, but you can use decision trees to do that, because you can see just from the data itself, you can see very clearly that whenever x is greater than 3, then all those data points right here are yellow. They are all yellow boxes. And when x is less than 3, then they are all right here in circles. It's a blue circle. So less than 3 is blue class and greater than 3 is yellow class. So that's quite easy to tell just by looking at the data. So let's see how you can represent this as a tree. This is what it will look like, what you see up here. This is our original data, all of it. This is the branch that we are creating, which is x less than 3. So all these blue points, they go in this section because they are all, as you can see, less than 3. And there's this partition created here at 3. So if it is greater than equal to 3, it goes to yellow. You can, of course, use the equal to sign with less than. With the less than sign, that's also fine. So you can decide if it is equal to 3, then should it be blue or yellow. So this was very simple and a very simple way to create a decision tree. So it's basically just defining rules that can help you to classify your data, or rather to form clusters. If you want to form clusters, you can use decision trees and just create rules and form those clusters. What happens if you have 3 classes instead of 1? So you can see here there are 3 classes. So even then, you can see there are some similarities with the 2 class one, because you can see if it is there are 3 partitions, but you can see that if a data point has the x coordinate greater than 3, then it is definitely a yellow class. And if it is less than 3, it can be either blue or it can be green. And that is decided on the basis of the y coordinate. If y coordinate is greater than 3, then it's green. If it's less than 3, it's blue, given that x is less than 3. So the same thing is represented here using a decision tree. This root node contains all the data points. Then we are dividing them based on x less than 3, x greater than equal to 3. If it's greater than equal to 3, it is yellow class. If it is less than 3, then all these green and blue are merged together. If you want to separate these two, then you just have to do y less than 3. If it's less, it is blue. If it is greater than equal to 3, then it's green. So fairly simple way of classifying or clustering data, as you can see. Now let's take a look at this algorithm, and I'm going to explain to you in the simplest way possible. So it won't be very fancy with a lot of formulas and all. It's going to be very much in English written sentences. So now, as we saw in our multi-class decision tree, we need to find a way to define these splits so that we find the best splits to identify our class. So we have several classes forming in our data set. And the key here is to define the split. Okay, from where exactly should you split? Should you create that split so that the classes formed are correct? Secondly, there's the added problem of finding the first split or the root because you're just starting and you have all the data points. Where exactly do you make that first split? Should we try every possible split to determine which is the best one? That can be exhaustive, but that's essentially what happens in a decision tree algorithm. You try each and every split, find the best one, and go with it. So now here, it's the same kind of data set, but little less points. You can see there are 4 blue, 3 yellow. And what I've done is for each data point, we've created one split. So you can see this blue one is in one split at 0.5. The second blue one is between 0.5 and 1. This one's between 1 and 2, 2 and 3. This is right here, 3 and 3.75. This is between 3.75 and 4.5, and this is beyond that. So this is the way we have created splits. So there are 6, yes, there are 6 splits over here, okay, because there are 7 data points. So we have defined 6 possible splits given our data that separate each point. Now, how do we know which splits are the best? Okay, because what we need to find is out of these 6, which is the best one? Should we take this? No, because then this blue one is going to be classified as yellow. Should we take this one? No, because if we do that, then this yellow is going to be classified as blue. So we have to try out all these splits and see which is the best one. And how do we know that? By Gini Gain calculation. This is a formula, very simple one, to find out which split works the best. So what is Gini gain? Firstly, we calculate Gini gain, and Gini gain is nothing but the impurity for the whole data set, which means if you are saying that this split is the one that you want to go with, then not this one's the best one, but if you're saying that this is the split you want to go with, then how good is that split? Because obviously, other than this split right here, every other split is going to cause errors. For example, if you choose 2, then there would be an error that this blue one is going to be classified as yellow. So that means this split is performing some clustering, some classification, but it is impure. And that's why Gini gain is used to calculate or sort of quantify this impurity of the split that you have selected. So this is the probability of incorrectly classifying a random selected element in the data set. Now, as you can see, if I were to select, say, this 0.5 as my split, do you think it would be, could you compare that with 2? Which one's better and which one's worse? Obviously, selecting 2 is much better than selecting 0.5 because when I'm selecting 2, at least 6 data points are correctly classified. But when I'm selecting 0.5, then only 1 data point is correctly classified. So that means there must be some probability. Now, this Gini index gives you that probability. If I have selected 0.5 as my split, then what is the probability that out of all these data points, I'm going to pick one, and that one is essentially going to be incorrect, is going to be incorrectly classified. So obviously, if I have selected 0.5, then this blue is correct. These 3 yellow ones are correct. But if I'm picking something from these 3, then it's going to be incorrect. So this Gini index or Gini gain is calculating the probability that if I selected this split, then and if I pick a random data point, what is the probability that it's going to be incorrectly classified? Okay, so here in the formula it is G initial because initially we're just calculating the Gini index as an initial value, and you'll see as we calculate it further. So here in this formula, which is sigma I equal to 1 to C, C is number of classes, and we have pi into 1 minus pi. Pi is probability of randomly choosing element of class I. Okay, so there are two classes, so we have to repeat this formula twice since we have I equal to 1 to 2. So let's see. So once again, here's the formula. Let's fill up all the values. C is equal to 2. Now, probability of an element of being of class 1, class 1 being, let's say, blue class. So how many elements do we have in the blue class? We have 4 elements here. So that means this is going to be 4 by 7. Total, we have 7 data points. So 4 by 7. Probability of the second class, picking a data point from the second class is 3 by 7. And just insert all these values into the formula and you can do the calculation. So you have G is equal to P1 into 1 minus P1 plus P2 into 1 minus P2, and just replace all the values there. You'll get 4 by 7 into 1 minus 4 by 7 plus 3 by 7 into 1 minus 3 by 7, which results in 24 by 49, and that is 0.49. That is our initial Gini gain. Now let's split the branches into 2 sections. So we're going to split it into left and right sections. And this is the section that we have selected, which is the 0.51. Okay, this first, essentially the first split. If you do that, then our left branch contains only one ball, which is blue. So if you're calculating just the Gini gain for the left side branch, it's going to be 0 because there is no other yellow ball, so that you have no probability to calculate. So it's just going to be 0. Okay, it will be 0 because we are applying the same formula, and anything you multiply by 0 is going to end up 0. So this is G left is 0. G initial was 0.49, and now for the right side. So on the right side we have 3 blue circles and 3 yellow circles. So the probability, 3 yellow squares, sorry. So the probability of the right side, that is G right, the Gini gain, is 3 by 6 into 1 minus 3 by 6, because there are total 6 balls and 3 are blue, 3 are yellow. So 1 minus 3 by 6 plus 3 by 6 into 1 minus 3 by 6, same, which gives us 1 by 4 plus 1 by 4, which is 1 by 2. So that means it's a 0.5. That is our G right. So we have 3 values now. We have G initial, which is 0.49. We have G left, which is 0. And we have G right, which is 0.5. We can now determine the quality of this split by weighting the impurity of each branch by the number of elements it contains. So you just have to find out how many elements it contains, and then you can calculate the impurity of each branch, which means you can examine each split that you have proposed to see how impure it is. So let's see. If you're trying to find out for the say the first split, which is right here, you can see. If you're trying to find out if this 0.5 split is good or bad, then what you have to do is just do 1 by 7 into 0, which is G left. 1 by 7 because on the left side of the split there is only one data point. And 6 by 7 because on the right side of the split there are 6. So 6 by 7 into 0.5, which is right. And that gives you 3 by 7, which is 0.43. Now you can remove this impurity from the Gini gain initial value, which was 0.49, and 0.49 minus 0.43 would give you 0.06. So essentially, higher this value, the better the split. So you're going to do this whole calculation again for each and every split that you have, and calculate this Gini gain value for each and every split. And the one that has the highest Gini gain is going to be the split that you will use. Now, calculating Gini gains is how we construct our decision tree. And if we have 3 or more classes, we just do the same with the other classes to form our second level of nodes. So first you're going to just create the first level by using the same procedure that we did. And then to create this level, you're just going to apply the same formula to this node right here for these values. So you're just going to go on doing that and creating a decision tree. We only stop doing that when our Gini gain, that is G impurity minus the impurity of our branches, is 0. This is because in our last leaves, there won't be any more classes to separate. So once you have reached here or here and you apply the Gini gain formula, you will notice that the G impurity minus impurity of any of the branches that you have selected is going to be 0. And this is because we are at the leaf node, and the data points are all belonging to the same class. Now, what are random forests? So once you know what a decision tree is, then random forest is going to make much more sense to you. So random forests are simply the output of multiple decision tree classifiers. So that means I'm going to explain that to you now in a bit. So you have multiple decision trees, and all the decision trees together, they give you, when you put them together, that's a random forest. So for random forest, we sample with replacement from our training data set, then train our decision tree on n set of samples, and we repeat this t times. Note some of the samples will be used multiple times in a single tree, and because it's a random forest. So now what exactly does that mean? So a training set is essentially the set that is already labeled and classified. So you already know that this is blue, this is yellow. Okay. And you're going to, from this training set, you're not going to use all the data points. You're going to randomly pick some data points. And that sample which you're picking is going to be a sample with replacement, which means once I pick a data point, I am going to put that same data point back into the pool and pick another data point. So there is a probability of picking the same data point again. Now, once that is done, once I have picked some data points, my sample is ready, then I'm going to perform the decision tree algorithm on this sample and create a decision tree. So let's say this is my first decision tree. Now, what do I do for the second one? For the second one, once again, I'm going to pick some data points at random and generate another decision tree, and so on. So you're going to do that for a set of n samples and repeat this t times. And once that is done, then all you have to do is just ask everybody to cast a vote. So how does that happen? First of all, if you have a new data point, the whole purpose of decision tree or random forest is to make predictions. So once you have classified your training data correctly, now you want to test your data set. So you want some data point which is not known to your model, and you want to introduce that data point and find out if that is supposed to be blue or supposed to be green. So assume there are two classes, blue and green. So is your data point blue or green? So what would you do? You'll ask the first decision tree to answer this question, and maybe that tree says blue. Ask the second one, says green, third one says green. And if you have 10 decision trees and 7 of them are saying green, then green it is. So you're just taking a majority vote. Okay, you're just taking a vote, and whatever the majority says, that is true. So that's how random forest works, and that's why it's very effective, because you're making so many decision trees at the same time. It is slightly slow, but you don't really have to code that much nowadays because of all the libraries available. I'm going to show you the code in a while, I'll just finish by telling you that this process of using multiple classifiers to find the most common output, which is the majority vote or average if it's regression, is known as bagging or bootstrapping. Okay, this is also called bagging or bootstrapping. And now we are going to implement a random forest for some data set that I have. It's fairly simple and won't take long. So let's do that. So this is once again my Jupyter notebook, and this here we are going to use this data set, which you can get from this link. I will link it down below. So this is the data set. You can see how it looks here. It contains the height and weight of certain number of people. I haven't calculated the length, so that's okay. And here the third label is male. So if it is 1, that means the person is male. If it is nothing, that means or 0, that means it's a female. Okay, so this is what we are trying to find out here. Is a person male or is a person female? So that is what is given here. It is all males. And if you just scroll down and see, these are all females. So these are the heights and weights of different people. And what we are going to do with the data set is to first of all perform a random forest algorithm and classify it. And after that, we are going to feed some values to it and just to see if it correctly identifies that as male or female. Okay, so now first of all, we are taking NumPy and Pandas libraries we are importing as usual. And this is a fairly simple code actually. This is the file which is available on GitHub. I will share the link. And then we are just reading this file, storing it into df, and we are printing some values which are the first 5 values from there just to see what it looks like. And then just plotting the data. Okay, let me run this. Next, we are going to plot our data. So this is how the plotting is done using Seaborn and Matplotlib. I think I've explained quite a bit of plotting in my previous couple of videos, so I'm not going to go into details here. But you can see the orange section is the male section, the blue one is the female section. And you'll notice that there is some cluster formed. You know, there's this blue section which is right here, and the orange section which is way over there. So you can notice that there is some cluster away. There are 2 clusters. Okay. I think I ran this. Did I? Okay, that doesn't matter. Now we are just going to get our data ready to prepare it for training in sklearn. To do that, you're going to use the iloc function. Now this function basically is used so that you can specify the x and y values. Y would be essentially the label that you want to use. For example, in this case, I want to classify my data as male, female. So that would be the second column of my data set. So that's why here you can see 2. And 0 to 2, which means all the values to be considered while you're going to train the data. So these are the 3 columns to be considered, and that is 0 to 2. So 0, 1, and 2 columns. Now you're going to split the data into training set and test set. Usually in most data science experiments, programs, we do an 80-20 split, which means 80% of your data is used for training and 20% of the data is used for testing the model that has been trained. In my case, I'm just going to take 0.3 here. So this is sklearn.model selection. It has this function here, train underscore test underscore split. So it allows you to split your data set into 2 parts, training and test. So there are 2 coordinates, x and y. So that's why we have x train, x test, y train, and y test. And here you have test size. So test size is going to be the size that you want to mention. So because it's 0.3, that means your training is 70% data and testing 30% data. And random state equal to 0 is, you may skip it if you want. Now this random, if you've already specified the test size, then the random state is going to be 0. If you do not want to specify the test site and want that to be something that's randomly selected, then you can specify that over here. Now we can import the random forest classifier from sklearn like this. Okay, let me run this. Okay, just import that into your Jupyter notebook. And then we are going to do the classification. So to do that, first of all, you're going to create an object of random forest classifier by writing this code right here. Okay, the name of the object is ran4_clf. And once the object is ready, then you're going to train your model. To train the model, you just have to do the variable you just created, object.fit, and pass the training data set, which is xtrain and ytrain, that is passed. And then you can perform your predictions. So to do the predictions, you're just going to do, once again, random forest underscore prediction. This is another variable that we have, and we are just going to use the variable we used earlier, the object. We are going to do that object.predict x_test. So now, because this model has been trained, it can now test these values. You could now do anything you would want with these values. It will return to you, bunch of zeros and ones, one for male, 0 for female. So you could plot it if you'd like. Okay. What I have done here is just passed my own values. Okay, so I just went ahead on Google and searched for the heights and weights of some of one female actress and of one female actor and one male actor. So, and then just fed the data right here to see what it shows. Now these two lines of code, which you can see, which is np.array, that is done because I need to create an array out of this to know whether to predict whether somebody is male or female. I need to specify the height and weight. So two values need to be given, as I have done here, but I do need to reshape it to be able to perform prediction using this classifier. And I have explained this thing a bit when I explained linear regression earlier. We did something of this sort back there as well. So np.array is going to create that array, and then reshaping is done with -1 and 2. I'm not going to explain this since I have already talked about it in one of the previous videos. And then we're just going to predict the gender. To do that, just pass this new variable array that you've created, pass it, and print the gender, which is coming 0 now. The height and weight I've used for an actress, Amelia Clark. I found that this is her height, this is her weight. Okay, so 157 meters is, now this data that we have is height in inches and weight in pounds. So I had to convert that, which I have done. 52 kg is 114.64 pounds, as I have mentioned here. Okay, and the height is 1.57 meters. We could convert that as well. So meters to inches. This is 1.57. Okay, that is 61.81. Hopefully that's what I have mentioned. Yes. So that is done, and you just print the gender. As you can see, it's showing 0. Was showing 0, it still shows 0, so that means it's a female. And let's try it for a male actor. So I'm going to go for Arnold Schwarzenegger. I tried it before. So, okay. This is, he is 1.88 meters. Let's just put that here. Meters into inches. 1.88. 74.01. We're just going to put it here. 74.01. And the weight is, it's already given here in LB, so I can use that. Let's just go with 235. Okay, so 235. And that's it. I'm going to run it. And it shows 1, which means male. So it has correctly classified that. And you could play with it and try a couple more examples if you would like. So that's it for this video. I'll be back with the next one. So I'll see you there, and thank you for watching.